The simplest idea that comes to one's mind in order to rectify this situation is to still carry out all the tests individually, but do something to change the level at which you are carrying out all the tests. And that gives rise to what is called the Bonferroni method of performing multiple hypothesis testing. Bonferroni's method. Now this technique is simply the following. You still carry out all the tests individually, but if you are trying to control the family-wise error rate at alpha, so alpha is something between 0 and 1, in that case you perform each of the individual tests at alpha by k level. So k is the total number of hypotheses that you are going to test. This is of course going to bound the family-wise error rate, because if you are going to reject at least one null hypothesis, that means if you consider the event that you have rejected the ith null hypothesis, you are basically considering the union of all these rejection events. So if Ri is the event that the ith null hypothesis is being rejected, then the event that n is greater than 0, number of false discovery is greater than 0, is same as union of Ri, and probability of that can never exceed sum of all the probabilities of Ri, that is precisely Bonferroni inequality, hence the name. And since each of them is alpha by k, and you have got k such things, so you get alpha by k plus alpha by k, k times, that is alpha. So the family-wise error rate will be less than or equal to alpha. So it does satisfy the condition that we wanted to have. However, this is far from a satisfactory solution, simply because, you see, if family-wise error rate is the only thing that you care about, it is something like you are caring only about type 1 error. You can always guard against that. You never reject any null hypothesis at all. You just blindly say accept, 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 accept. In that case, obviously, you will have no false discovery at all. Now, Bonferroni test is basically the same thing in a disguised form. Let's take our example of that coin toss thing. So, if we are trying to bound the family-wise error rate at 5%, and you have got 100 tosses, then alpha by k will be 5% divided by 100, that is 0.0005. And if you try to carry out a test at that stringent level, you are basically never going to reject the null hypothesis, except possibly in the very extreme case when you have just 0 heads or 50 heads. So except in the very low probability situation, you are not going to reject it at all. So effectively, you are always accepting it and then saying, yes, I am guarding against type 1 error, or what we are calling here as family-wise error. So somehow or other, we have to take into account the type 2 error thing also. If you just guard against one thing, you are likely to move to one extreme, and that is not what you really want to do. And that is why we need more sophisticated versions of multiple hypothesis techniques.